Thank you so much. I'm so glad I could present it to all of you and get a chance to chat with all of you virtually as it is distributed all around the world. But it's nice to speak without having to wear a mask. So there are upsides to these virtual meetings nowadays. And I do want to talk about the first stars to appear in the universe. And I want to talk about hunting them with radio telescopes, which is not exactly how you'd expect to naturally find stars in the very early universe. But first, I want to set the stage. It's always important that we understand when we're talking about hunting for the first stars, when we're doing these kinds of problems, this is a cosmological problem. This is a cosmological area of research. And so I want to make sure we all understand the proper context. So to start off, give me a thumbs up if you recognize this feature on the Earth. It might also be labeled here on Google Maps. That's right. So I'm based in the New York area. This is a very common sight. Has anyone ever been to the Statue of Liberty? Yeah, it's big. It's a very impressive, very beautiful statue. It's large. It's definitely a large thing. Naturally, we're going to look at things that are a little bit larger than this. So I'm going to zoom out. We're going to start here at the Statue of Liberty, and we're going to zoom out until we reach the scales that I'm talking about. So here we are. Can anyone spot the Statue of Liberty? It's a big statue. It's a big statue. It's right. You see the word New Jersey right there in the middle of the water in the Hudson Bay. It's up and left of the word new. Right there is where the Statue of Liberty is placed. So as soon as you zoom out just a little, it becomes very hard to see that big statue. And as we zoom out even more, it gets even hard to see New York. I mean, you can see the massive gray metropolitan area surrounding New York, but you can't distinguish the individual buildings. You can't, it's just the city itself becomes this almost indistinguishable blob. And once we zoom out all the way, like here we are in orbit, it becomes very hard to pick out New York City down there. And once we're out here, like a geosynchronous orbit, like all you see are continents, you see massive clouds, you see oceans. Even the biggest cities in the world become totally invisible from this distance. Now, the Earth, I would say, is pretty large, and I hope you would agree. You know, it's pretty big for a planet. It's the biggest of the rocky planets. We're big enough to have an atmosphere. We have liquid water oceans. We have this cool moon. Like, we've got a lot going on with planet Earth. It is a big planet. Yeah. Does anyone know where Earth is on this image compared to the sun? It's not the blue thing off to the right. That's Neptune. Earth is way over on the left. It's the third planet. You see tiny little Mercury and then a slightly bigger Venus, and then you see Earth. I hope this can give you some sense of just how big the sun is. A million Earths, over a million Earths, could fit inside the sun. And you know what? Our sun is a pretty big star as stars go. It's certainly not the biggest, okay, but it's larger than average. It's big enough to burn for 10 billion years. It's a nice sized star. Here's a typical nebula. A typical nebula has enough material to build 10,000 suns. 10,000 suns. Each one of these tiny little dots is an entire star. So when you look at a nebula like the Orion Nebula or the Cat's Eye Nebula or the Eagle Nebula, each one of those complexes has enough material to build thousands, if not tens of thousands of stars. And yet that is still not the scale that we are talking about. We need to zoom out even more. And here's a map of the Milky Way galaxy. You can see where our solar system is located. It's on the spur of a spiral arm called the local arm or the Orion arm. We're on a little sub arm attached to that spiral arm. The entire Milky Way galaxy is 100,000 light years across and is home to around 300 billion stars. We also, in the very center, have a supermassive black hole that weighs 4 million times that of the sun. There is a lot of stuff going on in a galaxy. Compared where we started with the Statue of Liberty to these kinds of scales, it is absolutely mind-blowing. And we are still not done. So I'm going to show you a movie. This movie is actually pretty old. It's about 10, 12 years old now. It's from the Sloan Digital Sky Survey. But I love the movie because it makes a very, very good impression. What you're going to see here is a map of over 500,000 galaxies. And it's going to start at the Milky Way galaxy and it's going to zoom out. So as we zoom out, I want you to keep in mind that each one of these galaxies is a real galaxy in its real position in the real universe. This is not a simulation. This is not an artist's impression. This is actual data. Each single one of these fuzzy blobs contains hundreds of billions of stars. We are zooming out now to the scale of hundreds of millions of light years on a side. And we're seeing something very interesting here as we zoom out, as we reveal the larger universe. I'll switch to a picture here so you can get a better sense of it. First, you'll notice these arcs, these like fan-like structures, especially on the right-hand side. That is because of the survey itself. These are optical telescopes. In fact, the Sloan Digital Sky Survey is based in New Hampshire. And what these surveys do is they stare at one spot in the sky over the course of a night. So they'll take slices out of the sky. And so that's why you see those fan-like structures. But you also, inside of the fans, you see this very intricate, very web-like pattern. We call this the cosmic web. You see long, thin filaments of galaxies, you'd see dense, rich clusters, and you see vast, empty regions known as the cosmic voids. This is one of the largest maps ever produced of our universe. This map, one of the largest maps ever made, containing over 500,000 galaxies, represents volume of the universe and less than 0.1% of all the galaxies in the universe. We have been doing these massive surveys for years and even decades, and we've barely scratched the surface. And one of the cool things about cosmology, about studying the universe at this scale, is that the further out you look in space, the further back you look in time. So at the very center of this image, where we're sitting on the Earth with our telescopes, the galaxies that we see close to us are relatively contemporary with our own galaxy. So the Andromeda galaxy is 2.5 million light years away. When it took 2.5 million years for that light to go from Andromeda over to us. So we're not seeing the Andromeda galaxy as it is today. We're seeing it as it was 2.5 million years ago, which is relatively recent when it comes to cosmological questions. The galaxies at the very furthest edges of this map stretch back to about 1 to 1.5 billion years ago. So those galaxies at the very edge of the map, those pictures that we have, are not the galaxies that we have today. Or they're not the galaxies as they are today. They're the galaxies as they were 1.5 billion years ago. So we can look back in time. It's like doing paleontology. The further back we look, the deeper we go into cosmic time. But next, I'm going to show you something that is even older, even more ancient, even more primordial than any of the galaxies in this image. This is a map, a picture of the universe when it was only 380,000 years old. The current age of the universe is around 13.8 billion years. So this picture taken when the universe was only 380,000 years old, that's like taking a picture of you when you were only 7 seconds old. This is an incredibly old map. And this map, this light, you see it in this eggshell or egg-shaped oval pattern. This actually represents the entire sky, but it's just been mapped and curved onto a two-dimensional plane so we can see it in all one picture, but this is the entire sky. What you're looking at is an image taken with microwave radiation, around a frequency of 1 to 200 gigahertz, if you're want to map that into some sort of frequency range. This is in the microwave. We call this the cosmic microwave background. This image, this light, is left over from the infant universe and has been soaking the universe ever since and continues to soak it today. And some of that light has hit our telescopes. This particular map was taken with the Planck satellite, which was in operation for a few years. About 7 years ago is when it was running and taking data and making its surveys. This light was released at a very, very special time in the history of the universe. When our universe was younger than this, the universe was very small and very hot and very dense. It was so small and so hot and so dense that it was a plasma, where atoms were disassociated. You just had nuclei floating around and you had electrons floating around. It was a hot, dense soup. But as our universe expanded and cooled, the electrons found homes onto their nuclei, were able to form the first stable atoms, and our universe became transparent. And the light that was bouncing around in the early universe was finally free to fly out wherever it wanted. And it has persisted for all those billions of years and continues to persist today. This cosmic microwave background is the brightest object in the universe. It is the source of over 99.99% of all the photons, all the radiation in our universe. This is it. This is the baby picture. And what you're seeing here in this map, you see these blue patches, these red patches. The big blue and big red patches that you see, those are due to sound waves that were crashing around the early universe, making regions more dense than average or less dense than average. These differences between the red and the blue, these represent density differences of less than 1 part in a million, but they were there. And though those left an imprint in the radiation that eventually came out. The small little bubbles that you see, the small little flecks of blue and red, those density differences are what will eventually grow up to become entire galaxies. So 13.8 billion years ago, this patch of the universe that is currently occupied by the Milky Way galaxy and you and me was once a slightly higher than density patch in the hot universe. Let me put this in context for you to give you show you the relationship between the cosmic microwave background, which you see here, and the galaxy surveys that you see later. This is a very, very broad cartoon overview of 13.7, 13.8 billion years of cosmic history, where we have the very early universe, which we don't fully understand, but we have some hints of what's going on. We have the release of this afterglow light pattern, or also known as the cosmic microwave background, when the universe was 380,000 years old. And then slowly, matter accumulates onto those dense patches. You know, they have a little bit more gravity than average. They're a little bit more dense than average. So they can slowly build material, building and building and building. And those become the first stars, which we think ignited around when the age of the universe was around 400 million years old. Then those first stars started to group together, the first galaxies formed, and then eventually that grand structure that we saw earlier emerges. But there's a phase here that we do not fully understand. We have the cosmic microwave background. So we have a picture of the universe when it was very young. And at the other end of the scale, in more recent times, you know, the past 1 or 2 billion years, we have our galaxy surveys. But there's a chunk in the middle that we don't have any observations of. And the challenge with observing this chunk in the middle, the first 1 billion years of the history of the universe is currently unexplored and unmapped. And there's a mystery here. There's a mystery of exactly what happens. We know that in this epoch, the first stars form, the first galaxies form, the first stars die, the first supermassive black holes come online. And after about 1 or 2 billion years, the universe looks a lot like the universe does today. But we don't fully understand that process. And there's something else funny going on in this epoch. When the cosmic microwave background was released, when our universe was a baby, when it was 380,000 years old, it transitioned. There was a massive phase transition that took over the entire universe. It turned from being completely a plasma, super hot plasma, to being a neutral gas. The electrons had bound onto their nuclei and formed atoms. It became a neutral gas. But when we look around at the universe today, we see almost entirely plasma. The sun is made of plasma, and the sun is most of the stuff in the solar system. You look at those pretty nebula, those are all plasmas. All the electrons have been ripped off. Neutral gas with actual atoms or molecules is actually very, very rare and very special in our modern day cosmos. So something had to happen. Something had to transform our universe from being completely neutral to being completely ionized, to become a plasma again. We call this transformation the epoch of reionization. The epoch of reionization overlaps with another thing we call the cosmic dawn, which is the formation and the appearance of the first stars and galaxies. Prior to this epoch, prior to reionization, prior to the cosmic dawn, we call it the cosmic dark ages. And the dark ages ended with the formation of the first stars, the formations of the first galaxies. Somewhere in there, in that first billion years, the universe became reionized. And that's because it used to be ionized, it used to be a plasma, then it became neutral, but now it's ionized again. Here is another view. Oh, whoops, sorry. I got rid of that slide. I forgot I got rid of that slide. We don't know what caused the reionization. We don't know what powered that last and final phase transition in our universe. We don't know how it happened. We have some ideas. Because again, we have no observations of this epoch. We have not seen the first galaxies. We have not seen the first stars. We have not seen in our telescopes this transformation unfold. It is a gap in our understanding of the history of the universe. Reionization could have taken place because of those first stars. The first stars we suspect were massive. They could have been easily 100 or 200 times the mass of our sun. They would have been huge. They would have been bright. They would have been spewing out ultraviolet radiation and X-rays. And then they die in massive supernova explosions. We know that the first generation of stars to appear in the universe died quickly because we don't see them at all in the present day universe. If we look around our own galaxy or nearby galaxies, we don't see any stars that are that old. And we test this, we know this because we can look at what the stars were made of, or stars are made of. Stars are almost entirely hydrogen and helium, and then there's a little sprinkling of other elements, heavier elements like carbon or oxygen or iron or potassium or whatever. The first generations of stars only had hydrogen and helium to work with, and maybe a little bit of lithium. That's all they had to work with. Inside of those stars, the first heavier elements were produced. In their supernova explosions, the first heavier elements were produced that got mixed into the next generation of stars. Then the next generation of stars made more carbon, more oxygen, more iron, more silicon. Then they died. Then the next generation had even more iron, more silicon, more lithium, more carbon, more oxygen, and so on. With every generation of stars in our universe, the amount of heavier elements grows and grows and grows. And so you can look out at all the stars in the Milky Way. You can look for stars that are purely hydrogen and helium, and we don't see any. So we know that this first generation of stars did die. We don't know how long they lived. We don't know how they formed. We don't know if they caused this epoch of reionization. They could be, because they were pumping out, possibly they were pumping out extreme amounts of ultraviolet radiation and X-ray radiation. And this high energy process could have soaked the universe in this radiation and blasted apart any neutral gas they could possibly find, reionizing the universe. But there's another potential source of reionization. And those are the first black holes. When black holes get big, we give them a very special name. We call them supermassive black holes. And supermassive black holes are big, like they're millions or billions of times the mass of the sun. We have one in the center of the Milky Way galaxy. Every galaxy has at least one supermassive black hole. And sometimes material, gas and dust, and even stars can fall onto that central giant black hole. When it does, it squishes down to form an accretion disk like you see in this artist's visualization. This accretion disk swirls around the black hole and can drive up extremely strong electric and magnetic fields. And these magnetic fields can take material and, instead of funneling it down through the black hole, can wind it around the black hole, wind it around the event horizon, and then send it off in these massive jets. We call these objects quasars, or if they're particularly powerful, we call them blazars. These jets, as you might imagine, release a lot of energy. When black holes are feeding, they can outshine millions of galaxies, so they can pour tons of radiation into the universe through these jets, and they could potentially be responsible for reionization, for turning our universe from neutral back to a plasma. But we honestly don't know. The first stars were far weaker than the black holes, but they were much more numerous, and they may have come along online a lot quicker. However, the black holes, even though they're more rare, they're kind of powerful. And so maybe they were more responsible for the reionization. So we want to hunt for the first stars. We want to hunt for the first galaxies. We want to see them so that we can map this out, so we can understand this critically important phase transition, the last great phase transition that our universe experienced, and really gave us the universe as it is today. We don't know the ultimate culprit. And it's hard to see because the galaxies themselves, one, during the Dark Ages, there were no galaxies, there were no stars. We can't see it with visible light. And then once the first galaxies come online, they're so far away and so dim that we can't see those with our telescopes and with our observatories. So there's a gap here, and it's right at that critical moment, at the end of the Dark Ages, the beginning of the cosmic dawn, the transition from a neutral universe to an ionized universe, we can't directly observe with any of our instruments. But this is where radio comes in. And it comes in a very, very curious way. Neutral hydrogen, which is just a proton and electron hanging out. Each one of these particles, the proton and the electron, have spin. They can spin in a particular direction. And the natural state, the state that neutral hydrogen prefers to be in, is with the proton and the electron having opposite spins. This is the lowest energy state of the arrangement of this system. But every once in a while, if you get enough hydrogen together, enough neutral hydrogen together, the electron, just because of quantum mechanics, will randomly decide to flip up and be parallel with the proton. Now, this is an unstable situation, so immediately it flips back over. But that transition, going from a higher energy state to a lower energy state, releases some of that energy. It's a purely quantum mechanical process, but it does release energy. It releases light, releases one photon with a very, very specific wavelength of 21 centimeters. 21 centimeters, or a frequency of 1,420 megahertz. This is the frequency emitted by neutral hydrogen. And why do we care about neutral hydrogen? Oh, like here's a map, a neutral hydrogen map of our own Milky Way galaxy. So you can see there is still some neutral hydrogen left hanging over, even though the majority of it is ionized. And you can see all sorts of cool, interesting structures in our galaxy of where the neutral hydrogen is. So we do astronomy with neutral hydrogen at this frequency. Why do we care so much about neutral hydrogen? Well, in the very early universe, during the Dark Ages, our universe was neutral. There were no stars, there were no galaxies, there was just cold, neutral gas. There was neutral hydrogen. It was emitting radiation at this frequency, at this wavelength, at a wavelength of 21 centimeters. Then reionization happened. The first stars came online, the first galaxies came online, the first blazars and quasars came online, and it wiped away almost all the neutral gas in our universe, and this signal disappeared. This emission is because there wasn't enough neutral hydrogen to make this happen. So we suspect if we look for neutral hydrogen, in the very early universe, there'll be a lot of emission from neutral hydrogen. Then as the cosmic dawn and reionization proceeds, that signal will go away. And that we can potentially use this to map out the history of reionization, to tell us how the first stars and galaxies formed and where they did and how they made this major phase transition in the universe. But there's a catch. There's two catches, actually. One of them is good, one of them is bad. The good catch is that we live in an expanding universe. Every single day, our universe is getting bigger and bigger. That's why in the very early universe, it was smaller. It was small enough to be hot and dense to create a plasma. And nowadays, not so much because it's bigger and older and colder. This expansion of the universe stretches out light rays. It stretches out radiation. If you emit some radiation today and let it go flying free in the universe, by the time it reaches its destination, it will have experienced some of this stretching from the expansion of the universe, and it will get bigger. Its wavelength will get stretched out. It will turn redder. The light that was emitted in the early universe because of neutral hydrogen started out with a wavelength of 21 centimeters. About yay big. But over cosmic time, over those billions of years, that light has been stretched out. And now that light has a wavelength of around 2 meters. And instead of having a frequency of 1400 megahertz, now it's around 140 megahertz. It's in the radio. So if we want to go hunting for the first stars, we have to look for the neutral gas. And in order to look at the neutral gas today, we have to look in the radio. And so radio telescopes around the world are being designed, are being targeted to hunt for this neutral gas. One of them, which you'll hear about more, is the Very Large Array. The Very Large Array is a very, very famous instrument. It's an interferometric telescope. So this saves you from having a single big dish and trying to engineer a giant dish that's like 5 miles across. You can instead have many, many smaller dishes, and you blend their signals together using interferometry. The VLA is trying to hunt for this signal. Here's a proposed network of dishes, an interferometer called HERA, the Hydrogen Epoch of Reionization Array. This is based in the a telescope as here is going to consist of over 500 dishes working in concert to try to find it out. In coming up in the next decade, this is another telescope array that is being designed. This is called a square kilometer array. This is going to be a network of telescopes that are split between the desert of Western Australia and the Karoo Desert of South Africa. This is a major international effort. The square kilometer array will have many, many, many science goals. One of them is trying to hunt for the first stars. So why do we need these massive telescopes and interferometric arrays to get at this signal? The big challenge is that neutral hydrogen from the early universe isn't the only thing emitting at that frequency range. 140 megahertz. Yeah, there's a bunch of Earth-based sources. I think 140 megahertz is used for emergency radio, especially marine emergency radio, if I remember right. 140 megahertz is produced in our own ionosphere. 140 megahertz is emitted by the sun. It's produced by stars blowing up. It's produced by our own galactic magnetic field. Like at 140 megahertz, the universe itself is incredibly loud at these frequencies. And this signal from the epoch of reionization is a tiny, 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 tiny whisper that is on top of all this loudness. Like imagine someone right in front of you screaming in your face, and someone on the other side of a football field is trying to talk in a whisper, and you're trying to hear them. The foregrounds, that's what we call these other signals. You could be an astronomer and very, very interested in all the other stuff that is emitting at 140 megahertz, but if you're interested in this older primordial signal, it's all junk, it's all contamination, it's all foregrounds, and they're all about 10,000 1,000 times louder than this signal from the epoch of reionization. So to date, we do not have an observation of the Dark Ages. We do not have an observation of the epoch of reionization. We do not have pictures of the first galaxies. We do not have pictures of the first stars. We do not have a map, a history tracing how our universe went from neutral to ionized. We do not have a picture of that major transformational epoch in our universe. Right now, we have a bunch of hopes and dreams and some plans for some giant radio telescopes. That is the end of what I wanted to present. So I'm going to end my screen share. Looks like there are plenty of questions already popping up. Rich, I didn't know if you would like to field the questions or I can read them myself.
Well, go ahead and read them if you do that, and I'll field them if you can.
All right, absolutely. We had from Edmund was the favorite part of my work. So I personally get to do a lot of research, but I focus so much on outreach, on writing, on speaking, on hosting shows like Rich mentioned. My favorite part of any outreach I do is getting to connect with audiences, getting to share cool things about the universe. Getting people excited about it. It really is fun for me. We have a question from Gary. Can the CMB density and homogeneity be calculated from any known equations, quantum mechanics, or is the level simply observed without being fully derivable? Like, okay, so Gary is talking about those bumps and wiggles that we saw in the map of the cosmic microwave background, those big splotches. And he's wondering, can we just see it and map it, or do we have any theoretical understanding of it? The answer is yes. We have very, very precise and very accurate and very good theoretical understanding of how the universe got its spots. We do this through a combination of quantum mechanics with a dash of relativity and then a lot of plasma physics that we can trace the early history of the universe, and different theories of the early history of the universe will make different predictions. We can run those through, and actually it's possible to predict a lot of this with just pencil and paper. You don't even need to make simulations of it. And you can predict what that cosmic microwave background sky should look like. You can't predict the exact splotches because there's a lot of random processes that lead to that, but you can predict the statistics of what we call the inhomogeneities, or I also call the splotches. And so yes, we have a very, very good understanding, and this is one of the key pieces of evidence we have for the Big Bang picture of the history of our universe, is because in the Big Bang picture, we're able to make predictions for what the cosmic microwave background should look like. And that's exactly what we see. Another question from Todd: would the 100 plus solar mass first stars have become the massive black holes that controlled the formation of galaxies? Very, very cool question. We suspect, certainly, that the first stars died in giant supernova explosions. They may have left behind big black holes. And those could have grown up to become the first supermassive black holes that then started playing around and messing around with their galaxies. One of the challenges with this picture is we keep finding giant black holes in the early universe. We have seen these quasars, we have seen these blazars when our universe is less than 1 billion years old. So the question becomes, even in the most massive stars, let's say it leaves behind a black hole 100 times the mass of the sun. That's a pretty big black hole. How do you go from there to being 1 billion times the mass of the sun in only a few 100 million years? That is a major challenge for astrophysics. This is currently an unsolved mystery of how the first giant black holes came to be. Was it through rapid mergers and accretion? Was it through some exotic process that formed them outside of forming stars? We honestly don't know, and we won't know until we get better observations and data from this epoch. Great question, Todd. Rosemary is asking, what radio signal would the first massive black holes give? If so, how are people looking for that? Great question. These quasars, these blazars, we don't see the black holes themselves. We only see the material around it giving off this intense radiation. This does appear in the radio. This is, in fact, how we first discovered objects like quasars and blazars, was in our first deep radio surveys of the universe. They are giving off intense radiation of all wavelengths. They are massively powerful. But because of those long, thin jets, you can get particles swirling around those jets, and that does emit a very characteristic radio signal. So we are hunting for them with radio interferometers. We are looking for them in the millimeter regime with instruments like ALMA sitting in the Atacama Desert in Chile. And then also they're emitting a lot of visible light, which we will hunt for with the James Webb Space Telescope. That looks like all the questions. Feel free to pop some more questions on if you'd like.
Right. I do have a question for you.
Yeah.
You were part of the Planck collaboration, coming up with the microwave using the Planck satellite. What was it called? It
was the Planck Observatory.
Planck Observatory satellite, and observing the microwave background. You guys came up with a age of the universe with distinct error bars. And yet there's another group who has done it with using supernova distances, who came up with the age of the universe with error bars, and none of your two didn't overlap, which I guess has caused the cosmology crisis in all the headlines. Can you give us sort of a status of who's winning?
Yes, absolutely. So like you said, one of the key things we try to measure is the age of the universe, is the expansion rate of the universe, just some fundamental basic facts. Through our observations of the early universe with Planck, which I was a member of, we're able to derive from our observations one estimate for the age of the universe. But that's not the only way to probe the age of the universe. That's not the only way to probe the expansion history of the universe. There are several different ways. Another one, a very common one, is to use distant supernova. When you use supernova, you get a slightly, I believe, older age of the universe than you do from the cosmic microwave background. And the uncertainties are small enough on each side that there is a relatively large disagreement between those. We have a few options here. Either we're not fully understanding the cosmic microwave background and the sources of uncertainty there, or we are not fully understanding supernova and the sources of uncertainty there, or we're getting something wrong with our cosmological models, with our current understanding of the nature of dark energy, how the Big Bang works at later times. So you have three options. Obviously, I'm a little bit biased because I did work on the cosmic microwave background. I will say that our observations of the cosmic microwave background are the observations made in general of the cosmic microwave background derived from Planck are the most precise measurements ever made in all of astronomy and possibly all of physics. It depends on how you count it. We worked really, 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 really hard to make sure we fully understood our uncertainties. The supernova result based on that's getting this different measurement is based on several dozen supernova and really critically hinges on the observations of 6 galaxies. So I'm just leaving that out there of who you want to believe. Do you want to believe the most precise observation ever made in the history of astronomy, or do you want to believe 6 galaxies? The supernova people say, though, those groups say that they want, and a lot of this is led by Sir Martin Rees, the Nobel Prize winner. Um, I feel like personally he's gunning for another Nobel. He wants this to be a problem. He really believes largely the community does not believe that the supernova data are reliable as they say they are. We think that there are larger uncertainties in that measurement than are claimed. But I am biased because I'm a big CMB guy.
Okay, I think another question popped up.
Yeah. Oh, I see it from Todd. Will observing the first stars tell us about dark matter and dark energy? Does it put limits on what they are? Observing the first stars and the first galaxies won't tell us much about dark energy because dark energy is something that's come online in our universe in the past 5 billion years. The first stars were happening and appearing before dark energy. But it will tell us a lot about dark matter because the formation of structure in our universe was actually driven by dark matter. In fact, you can't even form galaxies without the presence of dark matter, so we wouldn't even exist if it weren't for dark matter. So, looking at how the first stars formed, how the first galaxies formed, when they formed, how big they were, how they were arranged throughout the universe will tell us a lot about the nature of dark matter. There's a lot of information out there yet to be mined.
All right. All right. I think that's the last question. And it, you know, the too bad about the Zoom thing, you can't hear clapping in the background or cheering, but you know, I'll give it to you that I'd be outstanding lecture. Really enjoyed it, and yes, people put your hands up and let me know what you think. And
Thank you. Thank you.
uh,
I really appreciate it. I had a lot of fun chatting with you guys.
this